Welcome to the Wingtra LIDAR webinar. We're very excited to have this, take the opportunity today and speak with everybody. We're going to have some great guests and some good conversations. Just kind of first a bit of housekeeping to get started here. On the Wingtra side, I'm joined with Julian. Julian McKern, Senior Product Manager, and he'll be our slide deck controller and also lead the general conversations. So everybody knows we are recording this live. There will be opportunities to ask your questions, and we'll go through those and keep an eye on them and get to them in the end. And we're going to do a roundtable discussion. So please put your Q&As in. And also, we are recording this, so this will go back out via email to everyone who has attended. So Julian, shall we proceed? Again, I've already introduced Julian. He's our Senior Product Manager here at Wingtra. Myself, I'm Ben Snyder. I'm Wingtra's Training and Certification Manager here at Wingtra. We're going to have William Dillingham from Inertial Labs. He is a Product Manager. We'll have Ravi Sonja. He's the CMT LIDAR UAS program at McKim & Creed. And then also his counterpart, Justin Alschinger, CMS LIDAR Remote Sensing Analyst, also with McKim & Creed. So gentlemen, would you like to pop on?
Perfect. Thank you, Ben, for the introduction. Today, we want to talk about LiDAR, and we're very excited about bringing this payload to you guys. I have it here in my hand, and we've been working with drones for many years now, and we've been working with photogrammetry for many years, and we've seen how much value photogrammetry adds across many industries when it comes to progress monitoring, to earthworks, to really getting very good data about the terrain. But we know that there was always this missing link of being able to understand the terrain under the vegetation. And we know that there are stages when it's planning and design, when there's bidding, that we need to really know what the terrain looks like underneath the vegetation. So that's why we are bringing you today the Wingtra LiDAR. So the fastest mapping drone just got LiDAR. You can see there how fast it is to, in a few clicks, go from a vegetated area to just having the terrain. And we're very excited to come up with a system that provides us 3 centimeters of vertical accuracy to be very easy to use. You just plug it in as you do with any other of our payloads. You connect the USB-C and you're ready to go. You just go through the checklist. Any pilot can go out there, collect very good data, very good quality. And we are mapping more than 2 or 3 times more than any of the other drones out there in the market. So we're very excited also to bring this forward to you guys. This is the payload just came out a few weeks ago. So we are very happy to have here Ravi, to have Justin, to have William, who will talk more about the payload itself. Ravi.
Thank you, Ben. Thank you, Julian. Certainly appreciate the opportunity to be here today. And thank you, everyone, for attending. I'll go ahead and introduce myself. My name is Ravi Sonja. I'm a certified mapping technologist in LiDAR with the American Society for Photogrammetry and Remote Sensing. I'm also the UAS program manager here at McKim & Creed, and I'm based in Raleigh, North Carolina. My background is working with airborne LiDAR, specifically with unmanned airborne systems for about the last 5.5 years. Done a wide variety of different types of projects, everything from topographic mapping, transportation, DOT type projects, electric utility, as-built, PLS-CAD modeling, vegetation encroachment studies. Outside of that, I've got a lot of experience working with bare earth and building edits for countywide mapping projects, as well as drafting metadata for those deliverables that were sent back to the USGS 3DEP program. Justin, I'll let you go ahead.
Hello, everybody. Good morning and good afternoon. I'm Justin Alschinger. I am a CMS LIDAR remote sensing analyst at McKim & Creed, working with Ravi, and been in the LIDAR remote sensing photogrammetry world for 10+ years, working with manned aerial systems primarily, so kind of getting now into the unmanned systems with Ravi.
Very briefly, I'll introduce McKim & Creed. We are an employee-owned firm that provides a broad range of multidisciplinary engineering consulting services over the last 45 years here. We're about 850 employees spread across 26 offices here in the US. From a geospatial perspective, we do everything from traditional land surveying, which we're licensed in 18 states for at this point, aerial, mobile, terrestrial, LIDAR and imagery acquisition and processing. From an aerial mapping perspective, we do work all over the country. We're also doing GIS, hydrographic surveying, and subsurface utility engineering.
All right. Good morning, guys. Man, 340 people. I can't get that many people to show up at my birthday party. It's a good turnout. Quick introduction of myself. So I am one of our product managers with Inertial Labs. I did my undergrad at Virginia Tech, and it was nothing to do with LiDAR payloads. But I've had the last 5 years to mature some experience, primarily with inertial systems, mostly MEMS-based technologies, and Kalman filtering. And then really about 3 years ago, really started to dabble in and get well acquainted with the LiDAR mapping space. And I had to throw in a kind of a fun item. Something I like to do in my free time is hiking and mudding. I love off-roading in my truck. And jump to the next slide. And then some background on Inertial Labs, founded in 2001. We've got a strong base in research and development. Again, most things are all around kind of inertial-based technologies. We've got a little over 175 people. I think that's gone up about 20 people in the last 6 months or so. But our main experience, again, is in position, navigation, timing, kind of navigation, filtering, and sensor fusion.
Thanks, Will. So we do realize that there are a lot of folks on this webinar today with varying levels of experience and knowledge when it comes to working with LiDAR and imagery. So we felt it might be good to just kind of set a baseline for what LiDAR is versus photogrammetry and how those two compete in some respects and complement each other, really. So talking about LiDAR, which stands for light detection and ranging, it's using a pulsed laser in combination with a scanning mechanism. Generally, that's a mirror that's either rotating or oscillating inside of the scanner head. And these are active random sampling systems which generate their own source of energy. For that reason, it is agnostic as to when you can collect it. You can collect LiDAR day or night. Most LiDAR systems are capable of multiple returns from an outgoing pulse. And what's really happening there is a laser pulse is emitted, that beam has energy to it, it interacts with a target. If there's enough energy left over to continue on, it will continue on and interact with another target, and that's where you're deriving those multiple returns. Photogrammetry, it's really just a camera that relies on external lighting to be able to collect data. These are passive sensors, they're not generating their own source of energy. Generally speaking, we do try to acquire LiDAR in leaf-off conditions, but there are project timelines and different applications. For example, vegetation management for electric utilities, where that may not always be possible. And the good rule of thumb is if you're standing in a forested area and looking up at the canopy and can see sunlight coming down through, you're gonna have a pretty good chance of getting returns off the ground. And then I also, tying back into LiDAR versus photogrammetry, I do want to talk very briefly about LiDAR versus dense image matching. Dense image matching is essentially a photogrammetrically derived point cloud. This is typically done using an off-the-shelf software, something like a Pix4D or even Agisoft Metashape. I've got two pictures here on this slide. The one on the right is a dense image matching point cloud. It's colorized using the RGB values. You will notice there are voids around the footprints of the buildings, underneath the trees, and along some of the curbing features. This is the same area which was a simultaneous dual collect for LiDAR and imagery, and it is leaf off. And when you look at the LiDAR point cloud on the left, you'll notice it's displayed by intensity. The voids that were present in the dense image matching point cloud around the building structures and under the canopy and along the curbing are no longer there. That's really the main advantage to LiDAR, is you have this active sensor that's emitting a laser pulse that can penetrate down through vegetation to get to the ground. Ultimately, whichever one you use, whether that's a LiDAR or photogrammetric approach, really depends on the project specifications, the required accuracies, and the deliverables that you're trying to create from that.
Awesome. So I'm going to touch kind of a couple high-level applications, and then I think Robbie's going to jump back into some more nitty-gritty stuff. But I think kind of right off the bat, it's important to make note that for a lot of things, LiDAR is complementary to photogrammetry. It's not like the superior product. And this is really because of a number of different parameters, but for the Wingtra LiDAR solution, we see the largest benefits in really the large vertical field of view, a fast frame rate or update rate of the rotating laser head inside, and the fact that it has a maximum of 3 returns. The large vertical field of view means that there's limited gaps in data coverage. As we saw in the previous slide, there were some holes there when you ended up building out that map. But the large vertical field of view, kind of complemented with that fast update rate, means you get to see things on the forefront of scanning past it, and again on kind of the backside, you get an opportunity to kind of catch it at both angles and build out that map a little bit cleaner, and build out that penetration, as we like to say. That third point there is a maximum of 3 returns. This means you're more easily able to maintain maybe a required ground point density, and also ensure some reliability of coverage in gathering that lattice or structure work of the site that's being scanned. You can go on to the next slide. Another phenomenal application, again, a lot of this is really high level, is corridor mapping. And a lot of this boils down to some of the strengths that Inertial Labs has in bringing this solution with the Wingtra LiDAR payload. The inertials that are used inside of this system, they're low bias, they're low noise, low scale factor error, and that really does assist in making sure that what you're referencing is properly georeferenced. And when you're doing these kind of long, straightaways, you don't have to worry about drifting and needing to do additional convergence maneuvers over time. We also incorporate a very nice sensor calibration. We don't just account for kind of the IMU intrinsics with the LiDAR itself. We're actually calibrating each individual laser to the sensor inertial core inside. And really, at the end of the day, what this means you get longer missions without needing to do additional convergence maneuvers. You've got better reliability of your trajectory estimation. And then that ends up trickling down into the final, I guess we'll say final deliverable, but really the starting point for most of you guys, which is that point cloud. And having that better inertial inside means that you get to use not just the point that you're scanning right over, but also kind of the full swath width of the Wingtra LiDAR, which is right about 90 degrees. And that segues really nicely into our kind of next kind of high level application. If you want to jump into the next slide for me. And that's these large scale topos. Having better inertials inside means that you don't need to do strip alignment. We're doing a phenomenal job in our calibration, and also making sure that we're using the right sensor for the job. And those outer points where typically if you're using a lower cost inertial, they'd be really, we'll say, fuzzy on those outer edges. We're maintaining, centimeter level accuracy even on those outer edges, which means you don't need additional post processing that could be destructive in nature to the data set itself, which is really nice. This also means that you get to cover more ground and gather more data in a shorter period of time. I think Julian did a great job right at the get-go, letting you know that like 2 to 3 times better performance from a collection and we'll say saving time perspective. And some of the largest beneficiaries of this is really construction, mining, and precision agriculture, where the scale of those projects tend to be larger in nature. And I'll hand it back off to, I think Robbie's taking it over from here.
Great. Thank you, William, for this. I think it's super important, this what you were bringing in about the calibration, about how much time you save on the field because it calibrates on its own when it's doing the takeoff and doing the flight, but also how much time you save on processing. So thank you for bringing this data.
Absolutely.
Ravi, back to you.
Thank you. So, Will made some very good points there in regards to the number of laser channels in the field of view. And that, for me, really, that was one of the first things I wanted to look at when I got the sample data, before we were able to go out and conduct some of our own testing. The sample data that I have that's shown here on the screen, the top left and bottom right, those are single flight lines from the same project. This is a data set that was flown in Charlotte, North Carolina. For me, what I was really curious to see is, especially given it's a fixed wing application moving that fast, about 16 meters per second, I was very curious to see what that point density looked like for a single flight line. And I think what we're seeing here certainly supports topographic mapping and potentially even other mapping applications. A lot of that really is due to the 32 laser channels in the along track field of view. If this was probably, I don't know, 3 to 5 years ago, I don't think this would have been possible to do something like this on a fixed wing application. So it has been very good to see. If you could go to the next slide, please. So the main use case that we see this being suitable for here at McKimmon-Creed is really wide area topographic mapping. And from our perspective, the principles and the science behind LiDAR and imagery acquisition, as well as the processing, all of that really remains the same. We're really only changing the method of acquisition. So now we're going from a manned aircraft down to a drone. And everything Justin and I will cover here today, that is from the perspective of a geospatial firm that's following those best practices for aerial mapping. What you're seeing on the screen here is actually a screenshot of this Wingtra LIDAR system. It's visualized by the cut flight lines for the test site that we flew here in Raleigh, North Carolina. Next slide, please. And again, so we really look at this sensor aircraft integration as an unmanned fixed wing high density airborne LiDAR system for wide area topographic mapping. So from our perspective, what we wanted to understand is the sensor capabilities and the achievable vertical accuracy following those industry recognized best practices. I won't go through everything on the slide, but there were really two things that we were testing for and two things that we were trying to understand. And you know, what we're talking about today is probably in the neighborhood of about 40 hours worth of work between the field and the processing in the office that we're condensing down for today's webinar. So if you do have questions or is there something you'd like to know more about, please ask during the webinar. This is just a brief look at the site that we chose here. This was a 140-acre site in Raleigh, North Carolina that was selected for LiDAR and imagery acquisition. What we were really looking for as part of this test is varied terrain. We wanted hard, soft surfaces, you know, paved parking lots, roadways, buildings. We wanted some areas with short grass, low-lying brush and vegetation, as well as tall trees. This site really was great because it offered all of that in one area. From a canopy perspective, there was a lot of deciduous and coniferous trees, which really allowed us to evaluate the performance and the accuracy of the sensor. This data set was collected during leaf-off conditions, and there are a lot of pine trees in this site.
There are already some questions coming in. I'm very thankful for that. Some of them will come to you, Ravi, about the checkpoints that you're using. So we will address that in the next few slides.
Sure. And then this is just a brief look at the aerial targeting and control. We used a mix of chevrons, photo identifiable features, and panel targeting. We did find, we'll talk about this more later on, but the panel needs to be appropriately sized for the type of acquisition that's being performed. And then the last thing I'll mention about this is the control and the base station are all in the same datum for this project. And Justin will touch on that here in a bit. As far as the actual acquisition, we flew this at 80 meters AGL. It was originally planned at 60 meters, but because of a pine stand far off in the southeast corner of the site, we bumped it up to 80. 16 meters per second, 50% side overlap. You'll notice that we were doing north-south passes only. We were not doing east-west. We'll talk about that here in a bit as well. The resulting points per square meter, so nominal in a single swath, was about 86 points per square meter, and then aggregate, all the swaths combined throughout the project AOI was about 116 points per square meter. This site was completed for the LiDAR acquisition in about 15 minutes, and that included the dynamic IMU calibration at the start and finish of the flight. We know that some of the there can be issues that arise in regards to head and tailwind as well as crabbing in a fixed wing application. Realistically, if your airborne vehicle is crabbing that severely down a flight line, as a data producer, you probably shouldn't even be requiring LiDAR and imagery in those types of conditions. And I'll go ahead and turn it over to Justin from here.
Great, thank you, Ravi.
Thanks, Robbie, and again, hello to everybody. And so my role at McKinnon Creed is LiDAR calibrator, photogrammetrist, and all this other stuff. So I was tasked with kind of breaking down the data and really looking at it and seeing what kind of accuracies that we could get within the system. And then from there, seeing what kind of applications we could use. And so one of the first things that we usually do, that we do at McKinnon Creed in order to look at a LiDAR data set is looking at the line-to-line separation, seeing how well the flight lines are sitting with each other. And so in order to do that, one of the first things that we do is we cut the flight lines, and then this gives us the ability to run any type of strip adjustment within TerraMatch. This gives us the ability to run accuracy reports, both looking at the line-to-line separation as well as how the overall data set is looking compared to control points that were collected, as well as hard surface checkpoints, as well as vegetated area checkpoints. And so, so this was the first thing that we did. We cut the flight lines in order to run these adjustments to see what kind of accuracies that we were getting. And so if you go to the next slide, please. So kind of jumping right into it, when we ran our error assessment when looking at the line-to-line separation, initially what we found was that the error was around 2 centimeters. So this is how well the line-to-line separation was. So initially looking really good. We're in the centimeter accuracy range. And so after running our strip adjustments with there, we were able to tighten things down to get a line-to-line separation of about 1.7 centimeters. And so overall, looking at this, initially things look good. We were able to tighten things down a little bit more, but we're still in the 2 to 1.5 centimeter range when looking at the line-to-line adjustment. So really good stuff. So if you can go to the next slide. So how does this look visually across the entire project? And so on the left is the DZ initials, and on the right are the DZ finals. So looking at how the lines are sitting with each other in just a visual space. And so as you can see, initially things looked fairly good overall, with a few areas that needed some corrections. And then after we ran our corrections, we were able to reduce these errors across the entire project. And so really like the results from our processing here at McKinnon Creed. And so if you move on to the next slide, please. And so from there, we did some ground classification and manual editing. And so within TerraScan, we classified the grounds, the buildings, as well as low, medium, and high vegetation as part of our processing within the group here. And so to the next slide. And so from there, we wanted to see how well the data set was hitting to our control points, which Robbie talked about earlier. And so, so I'll just touch on kind of the one key finding that we found, that the initial accuracies, like most LiDAR data sets, usually vertically, they need to be debiased in some way. And so that means adjusting the LiDAR point cloud to our control points. And so we found that a debiasing was needed within this project. And so after we debiased the data, we had a final root mean square error of the elevation of 1.4 centimeters. And so really like that number, centimeters, great stuff. And so we're really happy with that. And so we can move on to the next slide. And so from there, of the resulting 1.4 centimeters in the root mean square error, we easily can derive 1 foot DEM as well as 1 foot contours. And we feel very confident about the accuracy and reliability of this data with that root mean square error. And so next, I will briefly kind of just touch upon we use that control in order to debias the data, but we also wanted to have some independent check shots. And so we have both non-vegetated areas as well as vegetated areas. And so for the non-vegetated areas, the key factor that we found when looking at the ground points only, we found a root mean square error of 1.2 centimeters, which is a little bit better than the control root mean square error. So really like those numbers. And then next slide, please. And then looking at vegetated shots across the area, we found a root mean square error of about, next slide, please. We found a root mean square error of about 5.9 centimeters across the area. And so overall, in the larger scope of the entire project, we really liked what we were seeing with the control points, the check shots, the line-to-line strip matching and everything like that. We were really impressed with what we were seeing, and now I'll pass it off to Ravi to talk about some of the deliverables that we could probably use in the future.
Great. Thank you, Justin, for all of this explanation.
Thank you, Justin. So, from our perspective, seeing what we've seen in this project example here, we feel the system would be well suited to support, topographic surveying. So supporting our land surveying folks internally here at McKim-Cree, supplementing their boots on the ground approach. Earthworks or mining applications. There's a project that we fly every month, which is a coal ash pond that's got berms around it where the grass tends to grow on the berm. And we have found in the past that there's some months where they cut the grass down and we can get a good surface from a photogrammetric approach, but there's other months where the grass has grown up and we can't get a surface on that berm. Another would be solar site development, which we do a lot of right now. Corridor-based mapping, transmission and distribution specifically. There are some considerations there you have to keep in mind with the laser system itself. Now, it's not a fault of Wingtra or fault of Inertial Labs. It's just a inherent characteristic of that laser head in terms of the ranging and intensity, and then potentially even water resources for hydroflow modeling. Those are the main ones that we've seen, and probably when we end up getting our system initially where we will utilize it.
Excellent. Thank you, Ravi. Thank you, Justin and William. This has been great to hear you. I was going to bring up a few questions and ask Ben to ask a few questions, but already the audience is asking a lot of things. So Ben, feel free to choose the questions and shoot it to Ravi, Justin, or William.
Yeah, thank you so much. I've been monitoring the questions and still am as they're kind of coming in. So I'm going to try to lump a few that will answer several because there are kind of some repeat questions. But kind of starting off with Ravi, could you talk a little bit more just about how you set the control and then expanding upon that, perhaps of the panel size that you found that has really worked well?
Sorry, I was muted. Yeah, I can definitely talk about that. So we set on that slide back there, acquisition design, if you could, one more slide up. There we go. So there is a control network there. What you're looking at in this screenshot is really the blue line represents the project boundary. We always buffer that by at least about 25 feet for flight planning and processing purposes. But you'll also see we've got chevrons and a panel target, and the control network was uniformly spread throughout the AOI. We're really trying to give a good coverage. A good analogy is trying to pin the data set down like a sheet of paper to a table so that if wind came from one side, it wouldn't lift on that side. But the control itself was set using base rover methodology. The base station coordinates themselves were derived through a 45-minute occupation. 2 days after that occupation, that data was submitted to Opus to derive the coordinates. And then as far as the actual control points, they were established with a 180 epoch observation the day prior to acquisition, and then revisited again the day of acquisition and observed again for 180 epochs. All those coordinates that we derived are left in grid. We're not changing any of those around or moving them to a ground in any way. And then as far as the checkpoints themselves, there's 28, like Justin mentioned, 28 NVA, 16 VVA check shots. Those were all 5-second observations. Most, if not all, I was out there when we were doing this project, when we were setting the control and when we were flying it. Most, if not all, NVA checkpoints are on a photo identifiable feature, either a turn arrow, a pavement marking line, a crosswalk bar, something like that. Ben, your question also about the control. We did find that as far as setting the targeting, if you don't have access to a PID, meaning a stop bar, or in that example on the far right, the crosswalk, the ideal paneling size is about 3 feet long by 1 foot wide for those chevrons. And we're setting those using a, I guess it's known as like a temporary roadway marking tape. And then the panel targets themselves, which is in that second image from the right, we did find that 2 feet by 2 feet is not an adequate size. Moving at this speed and with the intensities from this system, the intensity recordings from this laser head, we're not actually able to see that. But if we bump it up to a 4 foot by 4 foot, then we can see it at that point.
Great. We have another question asking about the ability to fly the LiDAR in the Wingtra 1 Gen 2 at night. Can answer this one just really quickly. Certainly, the LiDAR data is not dependent upon light to collect, and you could. The big thing here with that is obviously wherever you're located in the world, I'm not sure, but dependent upon what the regulations say and your regulatory body says about flying at night, obviously keep that in mind. Another question that I wanted to kind of hit on as well. It goes back to the strip aligning. Have a strip alignment. I have a few questions about that, like really no strip alignment, and then also I believe Justin, it was in your data where it was saying that you went ahead and did some strip alignment anyway. Was that just for testing purposes, and could you speak more on that?
Yeah, so we at McKinnon Creek, when we deal with any type of aerial LiDAR, whether it's manned or unmanned, within our workflow is some sort of strip alignment. And whether that is, a lot of strip alignment, in this case, there wasn't, we went ahead and ran it anyway. But as you notice, going from 2 centimeters to about 1.7, for some people, that's not a huge difference. But for us here at McKinnon Creek, we have the ability to do that. So we go ahead and do that for most of our projects. And then, doing the strip alignment also gives us visually, it gives us a really good sense of how the lines are lining up with each other. So if for some reason during acquisition, there is something goes, haywire with the IMU, or it doesn't connect with the base station, we can easily see some of those larger scale issues, pop out at us. So more of a QA QC kind of situation for us here at McKinnon.
Okay, thank you. And Julian, this one might be a good one for you. How is the calibration maintained during the flight when the Wingtra is banking and coming back along its flight line?
That for William, you said?
I think that might be a good one for you, or whoever would like to take it. William, you can take it as well.
I'll let him start, and then I'll close the fill the gaps.
Great. So what it does for those who are not familiar with the Wingtra takes off, does the transition from a vertical hover position to a cruise position. Then it does the some lines to go up to the mission height. Then it does the flight lines, and then on the curves it turns to get back into the line. So as Ravi was saying, like very, very good for mapping, because it maps long corridors and large areas very fast. Can you, William, explain that a little bit more about the calibration itself and what happens with the system itself?
Yeah, so there's a couple of different calibrations that happen over, I guess, the lifespan of the product. The one that we resolve on the forefront prior to the system ever getting to the customer is we align all of the sensing components inside to the entire, I guess we'll call it a system level axis. And really that's all aligned to the inertial measurement unit inside. So all the individual laser channels are all kind of precision aligned with the inertial system inside. And we do that in a dynamic application. So we'll go out, we'll actually fly it, we'll gather all these points, and then we'll precision align everything. A second type of, we'll call it calibration, that happens is it's really an automated calibration. And this is done with the use of a trajectory processing software. So Inertial Explorer, Novatel offers a wonderful processing suite that's actually used inside of the Wingtra LiDAR app for processing the point clouds. But what happens when the drone first gets put on the ground with the payload inside? You'll do this little static alignment where basically Inertial Explorer, it's measuring some initial biases of the inertial drift. And then as it goes into a takeoff, it flies throughout the air. It's using in tandem some of the dynamics that are experienced and various offsets from, we'll say, the gravitational G vector pointing down to kind of estimate, what's your pitch, your roll here, and kind of use a number of different smoothing algorithms and a number of stuff that's well beyond my pay grade to kind of make sure that the trajectory that's being estimated and applied to correct for any type of drift over the course of the flight is all well accounted for. And then you'll land, and it does a very similar kind of final alignment there as well to estimate, again, some of those biases and apply those to the entire data set. So hopefully that kind of answered the question on what's going on there.
Absolutely. Thank you. And also, we have a question coming in. We're going to kind of combine a couple. Just talking a little bit, can somebody speak a little bit more on the PPK side of things, of how it kind of ties in? And then also, what have you found so far? What was the software that was used to post-process some of this data? I think you did mention it, Ravi.
Yeah, I mean, obviously we've got a base station running on site locally, so that data is being processed here in-house. I mean, that's a Trimble R12, I think, that was used as the base station. The pre-processing software, Wingtra has some that comes with this system that can be used for the initial pre-processing to take your raw laser information and generate a point cloud out of that. From there, we're going into really a tear scan or tear solid environment. Justin did all the processing on this one, so I'll let him continue that.
Yeah, and so so all of the, like Ravi said, the pre-processing was in PC Master Pro, and from there, we move everything into a microstation TerraSolid kind of environment where we're using T-scan and TerraMatch in order to find tie lines, run any strip adjustments that we need to, as well as look at the line-to-line adjustments from there.
Great. And here's another one. Well, Julian, did you have something?
Yeah, I wanted to take several questions that are coming in regarding the payload itself. The payload weighs about 1 kilogram. And again, it's the combination of the sensor, the IMU, and the GNSS. And as Ravi was mentioning, we need a base station in every flight in order to be able to put all of this together. This is different from photogrammetry. Photogrammetry, you could use PPK or not use it, and then you use GCPs. Here, you need to use the base station in every flight. And the reason for it being heavy is that it has all of this very expensive and very accurate equipment that makes the LiDAR payload. And then there's a question coming in that if it also has an RGB camera, and we have decided not to put an RGB camera, so it's actually light enough to be able to map very large missions and to get accurate data in every mission. But also what we realize is that most of the customers who are flying out there with LiDAR and who would also like to have a colorized point cloud, they also want to have a good quality orthomosaic. And for this, you need to always have a very good RGB camera. And that's why we decided to not go for a small RGB camera, but rather really go for a good LiDAR that can map a big area in a short amount of time. And if you still want to have a colorized point cloud, you can do a second flight with an RGB camera. And then you have the point cloud from the LiDAR, the point cloud from the RGB, and you can also have a high quality orthomosaic.
Exactly. Yeah, that you nailed it. Those were going to be the few questions I was going to merge for you. So you were one step ahead of me, like always. That's awesome. Also, we had somebody asking, like, where can we see some of this data? You can also go to the Wingtra website and or just Google Wingtra LIDAR and it'll be your first result. And there's data there where you can that's already processed that you can play with and have a look around, as well as other data that you would be able to download. So please, after the webinar, feel free, go ahead. And the weight of the sensor, we've already covered that. Let's see, what's another one? And as far as like power line transmissions, Robbie, have either, or I guess maybe Ravi or Justin or William, have either of you gotten a chance to fly power lines yet? And are you kind of able to see the smaller guy wires?
I can speak to that. I'm kind of cheating with this because I've used this same laser head, just a different integration at a previous company I worked at. So I've had some experience with it. The size system works for mapping transmission wires. You have to be very careful about the AGL at which you fly. That's the primary driving factor to being able to pick up some of those smaller, either the static wire at the top or the guy wires in the ground. With this system, we did fly when I had, which by the way, thank you to Duncan Parnell and Wingtra for coming out to Raleigh and helping us with this. But we did have Duncan Parnell also fly 6 spans of transmission line with several dead end structures inside of it. So the drone was flying in a straight line, then turning to continue down the flight line. We did notice, for the most part, it looked good, but there were some spans where the static wire did not come through completely. I'm not quite sure what's going on there. We're going to probably try to find another set of transmission wires and fly them again at about a 60-meter AGL with the proper side offset left and right of that center line to see what we can determine whether or not it's usable for that. But if you're flying this on a multi-rotor application, yeah, as long as you fly at the correct AGL, you can pick up those features.
Excellent. And here's another question. And Ravi, this kind of goes back to one of the other use cases that you had mentioned earlier. So it might be a good segue here, where you were talking about the ash stacks and how the grass was covered in those at certain points of the year. And how have you found the application to do that, or at least, or possibly within your other experience?
Can you rephrase that question?
Sure. We have somebody who's asking a question. They're looking to inspect grassed over ash stacks. And how would you see that, or how would you determine that the Wingtra LiDAR might be able to cut through the grass a little bit and see the smaller holes?
Oh, I did. I think I saw that question. Yeah.
Yeah.
I'm not really sure if it would work for detecting, very small holes in the ground. But certainly as long as there's some things you got to keep in mind with mapping through vegetation. If it's very dense, thick, matted grass, something like you'd find in a marsh environment, realistically, you're probably going to end up mapping the top of that grass, if it's that dense. Stepping back to like the manned aircraft world, when we went out and did countywide mapping projects, like I said, we like to fly LiDAR in the fall and the early winter before the snow gets on the ground. If you end up in the spring and the snow is on the ground, it tends to kind of map that vegetation down. So at least you're getting something that resembles a ground surface, but it's not quite there. It would work to penetrate through grass. It just depends how dense it is. Finding holes, very small holes in the ground, I don't know.
Yeah. Okay. Thank you. And Julian, this might be a question for you. What would you say the longest corridor mapping could be done in a stretch with the current payload as it is?
That's a very good question, and it depends a little bit on regulations and how far away you can fly. We've managed to do 6 kilometers in one flight, pretty easy and quick. But it really depends on how much of VLOS and VVLOS operations you can do. So it I would tie that to every country and every type of operation. But if that's okay, I would also like to answer a few questions that are coming in regarding software. And thank you guys for bringing all these questions in. This is super interesting to discuss. The LiDAR does come with a Wingtra LiDAR app. So it's not part of the Wingtra Hub. Wingtra Hub will remain for photogrammetry. Wingtra LiDAR app will be for processing the data. And as I was mentioning before, you get the USB drive from the payload. You get the Rhinex file from your base station. And the Wingtra LiDAR app will create the point clouds. Then with the point clouds, you can export it in several different ways, but you can then take it to whatever software you want to work with the point cloud. So a little bit what Ravi and Justin were saying about Terrascan, you can take it to any software that works with point clouds.
And I see another question that kind of came in. I'm happy to take this one. It was like, Wingtra used to be very anti-LiDAR and pro-photogrammetry, or so it seemed. It just shifted a little bit. He's like, was this just a supply and demand decision? To kind of take this, I think, most of the time, photogrammetry is going to get you 60 to 80% of the way there in many different applications. But what it can't do, LiDAR is able to fill in the gaps. So that's just my enough to be dangerous answer. I don't know if Ravi or Julian or if somebody else would like to kind of talk a little bit more about that, just kind of the relationship between photogrammetry and LiDAR.
I would like to add that it's important also for us, or it was very important to manage to find the right LiDAR that could successfully deliver good data in every flight. So William, if you want to speak a little bit about where you guys are at today with Inertial Labs, because I think you've done a great job in making such a good product. Agreed.
Yeah, absolutely. I touched on this earlier, but I think Ravi would agree that it's really not, is LiDAR better than photogrammetry or at competition with each other? There's a right tool for the right job. And even in him building out that map, and I'm blanking on the three, what's the acronym? Was it a DIM? Is that what it was?
Oh, the USGS 3DET program? Is that what you're referring to?
Was it DIM? The slide right before me. Yes, it was a DIM. Like, there are certain conditions where photogrammetry will be able to more easily fill in the gaps as opposed to LiDAR. LiDAR needs to actually have a point fire on that particular surface, while photogrammetry can use meshing applications to kind of build out and interpolate, whereas LiDAR doesn't. So I think there's always going to be a right tool for the right job. But certainly we're hoping to continue to push the ball forward in making some solutions in the future that do give the ability to do some of these single flight missions and do photogrammetry at the same time you're doing LiDAR. Right now, to do that well, it requires like a full frame image sensor, which there are only 2 cameras, maybe 3-4 cameras tops on the market that have something that's not the size of needing 2 hands to hold it, and having that coupled with the payload that we've got offered right now just isn't practical for the current system. So most people will always be flying a secondary mission anyway. So to make sure we're maximizing kind of the longevity of that flight mission and get price to performance ratio down, I think it made sense to push with what we pushed.
Thanks, William. I have a question I want to answer here. There's several people who were asking about the altitude above ground level at which we're flying, and it really depends on how high you can fly. Ravi was already mentioning that they were thinking about doing a flight at 60 meters, and then they ended up doing it 80 meters. We found 90 meters to be a very good sweet spot, combining large area that you can map and getting very good data. It's interesting that after 120 meters, after 400 feet, it's hard to get good data on the side. So actually, the amount of area you can cover over 400 feet, it doesn't really change that much. It doesn't get better. So actually, 120 meters is actually the highest that we recommend to get good data, and 90 is even better because you have a better density per square meter.
All right. Yeah, I'm just looking through those as well. Forestry use case. And let's see, let's grab one other question here. I was trying to get caught up on. And just to kind of connect to this question as well, it says, does the required base station need to be connected to an RTK network, or can you use something else?
No, I mean, it does not. We just have when we did our collect here, and anytime we do LiDAR acquisition, the preference is to have a local base running. It's just doing static observation at a 1 second interval. Started about 15 minutes before the acquisition begins, run it for about 15 minutes after the acquisition ends. That is only if you're occupying a known point. If you do not know the point that you're occupying, you've got to run it for probably 2 to 4 hours ahead of time, do your acquisition, and run it for 2 to 4 hours afterwards, so that when you submit that to Opus, it's deriving a good position. I do want to also say, with LiDAR acquisition, that sensor is not talking to the base station. The sensor is running in flight, it's collecting its own GNSS data, and that is the base station data is used in post-processing to correct the trajectory too.
Thank you. And I know on the one project you had mentioned, it was about 40 hours and I think that was kind of all in with time spent out in the field, or even probably time spent flight planning, and then time spent out in the field, then with the actual processing of the data. Is there any way you could break that down any further as far as how much time was actually spent out in the field to collect that data, vice the remainder to post-process and get your actual deliverable?
Sure. If I had to break that down, it would probably, we broke up setting the actual targeting and, putting the PK nails in the ground and then coming back and observing everything, collecting check shots. That's probably going to be somewhere in the range of about 8 to 12 hours worth of time, realistically. As far as the actual acquisition, I think you're probably in the 2 to 4 hour range somewhere. We were doing LiDAR and imagery. These flights run pretty fast, we found. I'm actually kind of surprised at how much ground we can cover in a single flight. And not to go on a tangent here, but we just did our first live project in North Raleigh, and it was a 80-acre site. By the time we accounted for flying out and covering all the control points, we're at 240 acres, and that was done in 20 minutes with I think we still had 10 minutes worth of time that we could have kept flying. So the processing standpoint, Justin, I'll let you take that.
Yeah, and initially, I mean, this is the first time that we worked with this system, so it's learning the new software, learning like what ground coordinate system everything's in. So there's a lot of like us just learning everything. And so honing down a tight workflow from getting all of the raw material into the field, and then from my perspective, getting everything QA/QC calibrated and all this other stuff in order to pass it off to the production team. I could probably see anywhere, depending on the size of the project, anywhere from 8 to 15 hours of like process time to get it from the raw stuff all the way to our production team in order to make the deliverables. And of course, as time goes on, learning, tighter and tighter workflows, on my end in order to do that. So we could probably tighten that down a little bit, but I'd say 8 to 15 hours at the moment right now with processing time and QA/QC and everything.
Thank you. And also, Justin, you might be able to answer this one as well. Do you happen to recall in one of your slides where it said 7 of those checkpoints were actually rejected? Do you happen to recall why?
Yeah, so in the vegetated areas, 7 of them we found really have high residuals. And so some of the points that we noticed, they were taken in very dense shrub. And so some of those points, we suspected that the laser wasn't able to penetrate through the shrub in order to generate an accurate ground surface. And then also with some of the points in the vegetated areas, we noticed that the surveyor was pushing the rod tip down into the soil a little bit more than he should have. And so we're suspecting that some of the high residuals was coming from that. So kind of a combination of laser not able to penetrate some very dense shrub and making sure that the surveyor is getting an accurate sense of the ground within a vegetated area. And so those are some of the reasons why we rejected 7 of the vegetated points.
And you recall kind of what the distance between GCPs were? Or what you found has been working pretty well for you all?
I think Robbie might be able to help with this question. The distance in between, like horizontally, like kind of a ground coverage.
Yeah, just as from like a layout standpoint, I believe was what they were asking.
That's a very good question. I think it's really, there's no one size fits all answer for a control network. It depends on the project, the size, the geometry, the terrain that you're dealing with. For something like this, generally we will target a nice uniform distribution and even spread throughout the AOI. For a corridor-based project, you might put it every, I don't know, I'd have to go back and look at some of the stuff I've done in the past, but we would try to, for at least like a corridor transmission line, we would stagger the control down the right of way, just jumping back and forth across the right of way. I'm not sure on the spacing. It also depends on how you're setting that control, depends also on the number of lifts or flights that you have. When you've got multiple flights that cover an AOI, you do also want to try to have control between those lifts to help calibrate that area as well.
All right. So we're coming up on time. I guess we've got just about 2 minutes left. Julian, should we wrap or do we want to do one more? What's everybody feeling?
My favorite statement is someone said Ben should run for president.
I know.
He's got that voice. I trust you.
I'll need to change my green screen. So, Julian, how about you? What says you?
I wanted to thank Ravi, Justin, and William, and of course you, Ben. I think this has been great discussion, and the whole audience. I mean, all the questions that are coming in are great. Luckily, all the questions are also tied to an email, so we'll be working on answering all the questions that are coming up. But again, thank you for making this a great conversation.
Yeah, and thank you again to everybody for attending. To our panelists, thank you for taking time out of your day. We really do appreciate it, and we're so excited to have you on here and just to be able to talk about the Wingtra LIDAR. Thank you again.
Of course, guys. Thank you.
Thank you.
Awesome. Thanks, guys. That was awesome. That was fun.